Hi everyone, thank you so much for joining our talk. I am Amine Bennouna, a third-year PhD student at the Operation Research Center at MIT, and I'm going to present to you this very recent work on optimal machine learning and data-driven decision-making with Professor Bart van Parijs. So consider a general setting of stochastic optimization where we have a set of decision theta, an uncertainty that is distributed following some probability distribution, and then a loss function that will map every decision and realization of the uncertainty to some loss. And the goal is to find the decision that minimizes the loss that is taken in expectation over the data distribution. And this is a very general setting that includes, in particular, machine learning problems where we trying to fit a function to the behavior of covariates. In practice, this expectation is unknown as we do not know the probability distribution of the uncertainty. And what we observe is rather some data that is sampled from this unknown distribution of the uncertainty. And the goal is, just from this observation of the data, to approximate this unknown expectation. So perhaps the most natural and direct way to approximate this unknown expectation is to replace it with the empirical mean constructed with the data. So this is what is known as empirical risk minimization in machine learning and sample average approximation in optimization, and this is very, very popular and widely used. However, we do not really know how good is this approximation. As a matter of fact, it can be very bad, and this is what is known and very well documented as overfitting, and is also documented in many other fields as error maximization effect in finance, for example, and optimizer's curse in optimization. And so the question now is, can we do better than empirical mean? Can we do something that will protect against overfitting? And the answer, without spoiling too much, is actually yes, we can do better than that. So one solution to overcome overfitting is to add regularization, which is this orange term here. And this is already very famous in machine learning, where we have regularizations such as lasso, ridge, best subset selection, or the less popular but a little bit more elaborate sample variance penalization, where we penalize with the empirical standard deviation. And with all these choices of regularization, the key question is, what is the best regularization to add? And can we compare regularization between them? And ultimately, what is the best regularization that we can add when we have some given data? So another possibility to overcome overfitting is to consider distributionally robust optimization formulation, where we consider the worst case expectation when the distribution is taken in some uncertainty set. And then the natural question again is, what is the uncertainty set to choose? How to compare uncertainty sets between them, and what is ultimately the best uncertainty set that we can choose given data? Okay, so let's formalize the problem of data-driven decision-making. We have this stochastic optimization problem that we want to approximate, and we can write it as the minimization of some costs that depend here only on the decision theta and the distribution. These are really the two parameters on which this problem depends. And what we want to do is approximate this problem with just observed data samples. So what we observe effectively are the empirical distribution that is constructed from these samples and the data size. And so the approximation is, in the very general setting, a function of the decision theta, the empirical distribution that you observe, and the data size. And so what we want to do is approximate this minimization problem with another minimization problem that is a function of the observed data and the decision. So the examples are what we've seen before, which are ERM, SSA, regularization, or distribution robust optimization, but now it's much more general. We can have any function of the data and the decision. And the question is, what is the best possible approximation that we can construct of this stochastic optimization problem only using the data? So to be able to formalize this notion of best data-driven approximation, we need to specify what are the desirable properties of a formulation. So we'll identify two key properties of a good data-driven formulation. What's going to make a data-driven formulation good? First is the out-of-sample guarantee. So we want this in-sample approximation, this approximation of our true cost, of our true expectation, to guarantee a good approximation of the true cost. More formally, we want to have this inequality, which is the true cost, the out of sample cost that I'm going to observe eventually has to be at least as good as my estimation. So keep in mind that we want to minimize, so we want to have this true cost smaller than the estimation. So the estimation is an upper bound of what my real cost is going to be. So it's guaranteed. If I guarantee that it's an upper bound, then it gives me this out of sample guarantee on the performance. And because this is a random variable, the observed data, and therefore the observed empirical distribution, then I want to take this inequality into a probability and say I want this event to happen with a large probability. Okay? And to quantify how strong is my probability, I will use here this expression, exponential minus AT, where AT is something that I can really choose to be whatever I want. And this will quantify how strong, how conservative I want my prediction to be. Okay, let us see a little bit in a figure how would that look like. So imagine this curve is my true cost. And then this is my estimate that would take any distribution, give me an empirical distribution and give me some estimation. So because the empirical distribution fluctuates due to the randomness of the data, this prediction here, this estimation, will fluctuate around the nominal value. So what I want is that wherever the fluctuation, I'm always an upper bound with high probability. So when I take this fluctuation as high probability, which is here, I want to always be an upper bound. This is kind of what the guarantee is telling me. Okay, whatever realization of the data with high probability, I will always be an upper bound on my true cost. And what I want to avoid is estimations like that, like this estimator C2, where I have this region here which will correspond exactly to the overfitting region, where if the data realization is in these scenarios here, I'm going to estimate something that is worse than the actual true cost. So my true cost will disappoint me, might cause me these big financial problems or this very bad estimation just because I overfitted to the data. I estimated something that is too good compared to the reality of what I'm going to get at the end. Now the second property. So the first property is what I desire in my approximation. Now the second property, which is accuracy, is how I can compare two different approximations, and I want to compare them by the closeness to the true cost. So what is closeness to the true cost? We can define this formally in many ways. And the way we choose to define it is through regularization. So any approximation can be written as follows, can be written as a sum of the empirical mean plus some term that I would call the regularization. Okay, so this is exactly the regularization that we saw in the example. So empirical mean plus regularization. And then I want to say that an approximation is better than another approximation by this inequality, right? This is better than the other approximation. If the first one, like C1, will add less regularization than C2 uniformly for whatever generation of the data and whatever decision. And I can write this mathematically and formally with this following formulation. But keep in mind that the intuition is that we want to compare regularization. And why do we choose regularization? It's because this is a rather strong property, and we show actually under some assumptions that less regularizations imply also less bias, implies less L1 error, and many other desirable properties that we want to have in our estimation. So again, how does this look like in a figure? If this is my true cost, and then I have these two approximations, I can say that C1 is better than C2. The blue one is better than the orange one because it's always lower than the orange one, so it adds less regularization to the true cost. And also another way to see it intuitively is that this is a better upper bound. C1 is a better upper bound than C2. And remember, we always want it to be an upper bound for the out of sample guarantee to be verified. So I want to have the smallest upper bound. But this is a rather strong notion of order between approximations because we cannot all compare them. This is a partial order, not a total order. For example, this green approximation here cannot be compared to the other approximations as it is not uniformly better than any of them or uniformly worse than any of them. So what we want ultimately is some strongly optimal solution in the sense that it is going to be So feasible, verify the out-of-sample guarantee, but also uniformly better than any other possible approximation that will verify the out-of-sample guarantee. And it would look something like this red approximation here. So more formally, the problem of optimal prediction is, given some desired out-of-sample guarantee, what is the approximation with the least regularization that will verify this guarantee? And I can write this as a meta-optimization problem, so I want to minimize over the regularization all the approximations that will verify the out-of-sample guarantee. Okay, and keep in mind the generality of the setting. I'm considering any function, and more precisely, which we detail in the paper, we consider regular functions to avoid some pathological examples. So for any function, any regular function, and any desired guarantee, we want to find what is the best formulation. So it doesn't necessarily exist, and actually it's very surprising if it exists. So we actually show that whatever choice of AT, a strongly optimal solution, such strongly optimal solution always exists. And we distinguish three regimes. The first one is when we desire very strong guarantees. So this AT here is very big than T, which means this quantity here decreases much stronger than exponential. So in this regime, we cannot do better than estimating the worst case scenario. Our estimation will be the worst case scenario of the loss of the uncertainty. Now, what if we desire a little bit weaker guarantees? So we'll desire exponential guarantees, where AT is essentially R positive constant times T. So this quantity decreases exactly exponentially. Then we show that this strongly optimal solution, in other words, what we cannot do better than, and actually the best we can do, is a distribution in robust optimization estimation with KL ball uncertainty set with exactly radius R. And the interesting thing is that the transition between these two is smooth, in the sense that we can see that this regime is exactly the limit of this regime when R goes to infinity, as the KL ball with radius R, ultimately when R goes to infinity, converges to the simplex, which we get exactly here. We consider the worst case distribution among any possible distribution, which is equivalent to the worst case loss of the uncertainty. Now, if we decrease further the desired out-of-sample guarantees, we want AT to be smaller than T, for example, log T. And therefore here we can have, for example, polynomial guarantees. Then the optimal estimation is SVP, sample variance penalization. So it's regularization with the empirical variance, square root empirical variance, so empirical standard deviation, with exactly the scaling, which is square root of 2AT divided by T. And we also show that this SVP, this penalization, this regularization, is exactly equivalent to a distribution robust optimization estimation with an ellipsoid uncertainty set, which is more precisely the Pearson divergence uncertainty set with this exact radius, which is AT divided by T. And again, the transition happens smoothly between the exponential regime and then the sub-exponential regime, because we can see this ellipsoid here as the second order Taylor expansion of the KL ball. Now, an interesting remark is that in both these regimes, super exponential and exponential, so these are strong guarantees, we get very conservative estimators, in the sense that both of these do not even depend on the data size. Whatever data we have a fixed ball where we of conservativeness. We do not converge ultimately to the true cost, and we always have this fixed level of conservativeness. However, when we get to the sub-exponential regime, a phase transition happens, and then we have a consistent estimator, a consistent formulation, as this term here, regularization, goes to 0, because AT is smaller than T, so AT divided by T goes to 0, and also the radius of this ellipsoid goes to 0, which means ultimately we converge to the true cost. We also show a quite, what I find, rather surprising result. We show that this quantity here, this penalization, is convex, while many people thought it was not convex actually. So why is it surprising? Because the empirical mean is convex, when the loss is convex, of course. But the empirical variance is not necessarily convex, even if the loss is convex. So here we are summing a convex and a non-convex function, which in general should be non-convex. But here we show that they both merge nicely, and they give us at the end a convex function that is actually easy to minimize. Finally, I want to also point out that we can also study a more precise but also more complex problem where instead of comparing the approximations just on every single decision, we'll compare them exactly on the optimal decision. So I will add a minimization here and everywhere, whether it is for the guarantee or for the order we define. But we show that even in this case, every result that we show still holds. It's more complicated, and also the proofs are more complicated, but the results all essentially hold. So in summary, traditional machine learning and operational research existing work try to first construct data-driven formulations of stochastic optimization problem, and then prove out-of-sample guarantees on this approximation. Our work does exactly the opposite of that, which is first, we set a desired performance guarantee, and then we construct the best data-driven formulation that will verify this guarantee. So we have a paper on all this work that is online now in archive, and we very much invite you to read it and send us any comments or questions if you want to discuss. We'd be very, very happy to discuss. Thank you so much.